We're going to call this video Implicit Differentiation 101. We will begin this video with a review of the chain rule. Recall h of x is equal to f of u. This statement speaks volumes. If I am beginning with a function of x and I have f of u, we can pretty much be confident that u is also a function of x, and we will let u equal g of x, as we have done multiple times previously. Therefore, h is this composite function, f of g of x, where u is g of x. Now we simply, if we want to find the derivative of h of x, we will use the chain rule. And h of x, the derivative of h of x, as we well know, is f prime of g of x times g prime of x. The derivative of the outside at the inside times the derivative of the inside. Note here, would like to make a special note that g prime, since u is g of x, we can certainly call g prime du dx, and we have used this notation many times before. Fairly straightforward, a brief review of the chain rule. We can certainly make that statement since du dx is g prime of x. So let's recall simple differentiation rule. H is a composite function of x. In fact, h is f of g of x. The derivative of h of x, h prime of x, is f prime of g of x times du dx. The derivative of the outside at the inside times the derivative of the inside. In like manner, go to the next slide. Again, I have h of x is equal to u cubed. Here, since I'm writing h of x, I'm assuming that u is a function of x. And since I have it written as h of x, that's a pretty good assumption. In fact, it's a true statement. U is this function of x, and we again will call it g of x. The only difference between this slide and the previous slide is I'm going to throw that differentiation operator in there just to let you know the action that I am performing on h of x and u cubed. This will be of importance as we go down the road. So I'm differentiating h of x with respect to x, d dx of h of x, and I'm differentiating u cubed with respect to x, d dx of u cubed. Just like before, this derivative, h prime, is going to be the derivative of the outside. Here the outside is u cubed, something cubed, is going to be 3u squared times u prime, where u is this function of x, and u prime is g prime of x. And as we did before, we can certainly easily call u prime du dx because u is this function g of x. U is a function of x. So if I'm talking about u prime, I certainly can talk about du dx. What I would like for you to observe is the right side of these three equations, specifically what is circled here. So I apply the differentiation operator, d dx of u cubed, and I ended up with 3u squared du dx. Why? Because of the chain rule. Let's see what else I have here. And what I want to do here is I want to start off the same exact way, except for one thing. Instead of using this dummy variable u here, where u is this function of x, I'm going to put y in. Keep in mind they're both variables. So this will be the statement that I have. I have h of x is equal to y cubed. Now I am assuming, again, since I am starting off with h of x, I'm assuming that y is this function of x, g of x. In like manner, I apply the differentiation operator on this d dx of h of x, d dx of y cubed. Again, the derivative of this left-hand side is h prime, and the derivative of the right-hand side is 3y squared, where I made this a strong assumption that y is this function of x, g of x, and y prime is g prime of x, and dy dx is g prime of x. This is all notation that we have used prior. The difference between this set of equations and the prior set was instead of u, I used a dummy variable y. And again, I would like for you to observe the right-hand side of these three equations. Y cubed, I differentiated y cubed with respect to x, and the derivative of the outside of y cubed was 3y squared dy dx, because I had to differentiate the inside. What was the inside? The inside was y is equal to g of x. Y was this function of x, which it had to be because h of x is denoted as a function of x here. Y prime, g prime, dy dx is g prime. Looking at the right side of these three equations and the right side of the prior differentiation problem, let's look at this particular example here. Let's move that guy out of the way for a moment. Now we have d dx of 3y to the fourth, and we are going to make this strong assumption here. And now I haven't started out with h of x or s of x or t of x. All I'm doing is differentiating this creature 3y to the fourth with respect to x. And I am making a strong assumption here, by all means, that y is a function of g of x. Y is equal to g of x. If that were the case, then dy dx would be g prime of x. And I think it is, from the prior examples, fairly straightforward for us then to see that if I'm going to apply the differentiation operator with respect to x on 3y to the fourth, I would get 12y cubed dy dx. The derivative of the outside at the inside, the derivative of the inside. Let's try one more example. And we have the derivative with respect to x of sine of y. And here, again, we're going to make a strong assumption here that y is a function of x. And it's going to be the inside. I think it's easy to see that y is the inside. And the derivative of y with respect to x, and I want this with respect to x, would be g prime. We don't know what y is, but we're just assuming that y is a function of x. But if I'm going to apply the differentiation operator with respect to x of the sine of y, I have to do something with the inside. And I'm assuming that the inside is a function of x. So the derivative of this is going to be the derivative of the outside, which is cosine of the inside, which is y, cosine of y, times the derivative of the inside, dy dx. And this, my friends, is basic implicit differentiation 101. We will follow next time with the video on differentiating an equation in XY land.